In 1650, a mathematician in Bologna named Pietro Mengoli wrote down a question that looked almost childishly simple. Add up the reciprocals of the squares 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 and so on forever. What number does that sum approach? You can compute the first few terms on the back of a napkin. After 10 terms, you get 1.549. After 100, 1.634. After 1,000, 1.643. The sum is crawling towards something, a real number sitting just above 1.64. But what is it? What number exactly? Mengoli could not find it, and over the next 85 years, neither could anyone else. Jakob Bernoulli, in Basel, tried and failed so publicly that he turned the failure into a challenge. In his 1689 book on infinite series, he wrote, quote, "Great will be our gratitude if anyone shall find and communicate to us that which thus far has eluded our efforts." End quote. His brother Johann tried, Leibniz tried, Stirling tried, de Moivre tried. The best mathematicians of an entire generation hammered on this sum, and they all came away with the same thing, a decimal, a numerical value, trailing off after the comma, with no closed form, no clean expression, no deeper meaning, just a number, just 1.6449. The problem got a name, because Basel was Jakob Bernoulli's city, and because the Bernoullis had beaten their heads against it for a generation, mathematicians started calling it the Basel problem. And the Basel problem sat there, unsolved, for 85 years. Before we solve it, let's understand it. The sum is a partial sum sequence. Call it S sub n. S sub n equals 1 plus 1 over 4 plus 1 over 9, all the way out to 1 over n squared. Every term you add is positive, so the sequence is monotonically increasing. Every term is smaller than the last, shrinking like 1 over n squared. Does it converge at all? You can prove it without blinking. Compare the sum, term by term, against the integral of 1 over x squared from 1 to infinity. That integral equals 1, so the tail of our sum, from term n onward, is bounded by 1 over n. The sum converges. It lives somewhere between 1 and 2. That much the Bernoullis knew. They knew the sum was a real, finite number. They could compute it to as many decimals as their patience allowed. Euler himself, as a young man, computed it to 6 decimal places by hand, 1.644934. 6 decimals is not a proof. 6 decimals is a decimal. It tells you the sum exists, and it tells you roughly where it sits, but it tells you nothing about what that number is, or why that number, or whether the number is rational or irrational, or algebraic or transcendental. The decimals were a wall. Everybody who tried to push past the decimals bounced off. The problem needed a new idea. And in 1734, in the same city where Jakob Bernoulli had first posed it, a 27-year-old named Leonhard Euler had one. Euler's idea is one of the most beautiful leaps in the history of mathematics, and it starts from a move so bold that the mathematicians of his generation did not think it was legal. Consider the sine function, sine of x, a smooth oscillating wave that passes through 0 at x equals 0, at x equals pi, at x equals negative pi, at 2 pi, at negative 2 pi, and so on. Infinitely many zeros, spaced at multiples of pi. Now Euler said, imagine sine of x was a polynomial, not a real polynomial. Real polynomials have finitely many roots. But imagine a polynomial of infinite degree with exactly those zeros. If a polynomial has roots at r1, r2, r3, and so on, you can factor it. A polynomial with roots at r1, r2, r3 factors as a constant times the product of 1 minus x over r1, 1 minus x over r2, 1 minus x over r3, and so forth. The constant is fixed by the value at 0. Euler took that factoring rule and applied it to sine of x, except he divided by x first to kill the root at the origin. He wrote down that sine of x over x equals the infinite product, for n running over every non-zero integer, of 1 minus x squared over n pi squared. The pairing of positive and negative roots turns the linear factors into quadratic ones. This was not rigorous. It was not justified by anything in the mathematics of 1734. Euler was treating a transcendental function like a polynomial, and nobody had proved you were allowed to do that. Weierstrass would not prove it was legal until the 1870s, more than a century later. But Euler did not wait. He pushed. Here is the trick. Euler had two different expressions for sine of x over x, and he knew they had to agree. The first was the Taylor series, which had been known since Newton. Sine of x equals x minus x cubed over 6 plus x to the 5th over 120 minus x to the 7th over 5040, and so on. Divide by x. The series for sine of x over x is 1 minus x squared over 6 plus x to the 4th over 120 minus x to the 6th over 5040. Every term is an even power. The second expression was his infinite product. Sine of x over x equals the product over positive integers n of 1 minus x squared over n pi squared. Two expressions for the same function. Expand the product. The lowest order term is the constant one. The next term, the coefficient of x squared, comes from picking the minus x squared over n pi squared term from exactly one factor, and the one from all the other factors. You do that for every possible choice of factor, and you sum. So the coefficient of x squared and the product is the sum over all positive integers n of minus 1 over n pi squared. Pull out the minus 1 and the 1 over pi squared. You get minus 1 over pi squared times the sum over n of 1 over n squared. Now match. The coefficient of x squared and the Taylor series is minus 1 over 6. The coefficient of x squared and the product is minus 1 over pi squared times our mystery sum. Those two coefficients must be equal. Minus 1/6 equals minus 1 over pi squared times s. Solve for s. Multiply both sides by minus pi squared. The sum equals pi squared over 6. Stop. Stop and let that land. You started with nothing but the positive integers. 1, 2, 3, 4. You squared them. 1, 4, 9, 16. You took the reciprocals, 1 over 1, 1 over 4, 1 over 9, 1 over 16. You added them up forever. And out of that sum, a sum about integers, a sum with absolutely nothing to do with circles or angles or trigonometry, out drops pi squared over 6. Pi is the ratio of a circle's circumference to its diameter. Pi shows up in circles, pi shows up in trig. Pi has no business being in a sum of reciprocal squares of integers, except it does, because it is. Pi squared over 6, numerically 1.644934066. Plug in a calculator, it matches the decimal the Bernoullis were grinding out digit for digit. It had been pi squared over 6 the whole time. For 85 years, the mathematicians of Europe had been computing the first few digits of pi squared over 6 without ever realizing what they were looking at. So where does the pi actually come from? Look back at the proof. The integers come from the series side. The sum runs over the positive integers, which are the indices of the terms. Fine. Where do the integers go into the product side? They go in as the zeros of sine. Sine vanishes at 0, at pi, at 2 pi, at 3 pi, and the nth zero is at n pi. So the number n pi is what lands in the denominator of each quadratic factor. The integers enter the product as the positions of the zeros of sine, measured in multiples of pi, not in raw units, in units of pi. And that is the whole trick. Pi is the ruler. Pi is what you have to measure the zeros with in order for the zeros to be evenly spaced on the integers. If sine had its zeros at 1, 2, 3, 4, the pi would disappear, but sine does not. Sine has its zeros at pi, 2 pi, 3 pi, and that pi has to get squared when you square the denominator, and that is the pi squared that shows up on the right-hand side of Euler's identity. The sum of 1 over n squared is asking the integers a question, and the integers, to answer it, have to walk over to the circle and borrow its constant. Pi is the phi. That is why pi appears where no pi has any right to be. Euler did not stop at s equals pi squared over 6. The moment he had his method, he ran. The sum of 1 over n squared is what we now call zeta of 2. The Riemann zeta function, defined as the sum over positive integers n of 1 over n to the power s for real or complex values of s. Zeta of 2 is the Basel sum. Euler's answer was that zeta of 2 equals pi squared over 6. He did not stop there. Using the same coefficient matching trick on higher order terms of the sine product, Euler computed zeta of 4, which is pi to the 4th over 90. He computed zeta of 6, which is pi to the 6th over 945. He found a general pattern. For every even positive integer, zeta of 2k is a rational multiple of pi to the 2k, a clean closed form. Every single even value of the zeta function. And zeta of 3, zeta of 5, zeta of 7, Euler had no formula for them. Nobody does. The closed form for zeta of the odd integers is one of the oldest open problems in analytic number theory. We know zeta of 3 is irrational because Roger Apéry proved it in 1978. We do not know if it is transcendental. We do not know anything like a closed form. In 1859, Bernhard Riemann took Euler's zeta function and extended it to the entire complex plane and wrote down one sentence about its zeros. That sentence is the Riemann hypothesis, and it is the most famous unsolved problem in mathematics. Every piece of that arc, every chapter of the zeta function story begins at the Basel problem. It all began with Euler staring at a simple sum of reciprocal squares, refusing to accept that the answer was just a decimal. The Basel problem is one of the cleanest examples in mathematics of a specific kind of miracle. A question that lives entirely on one side of mathematics, the arithmetic side, the integers, the counting numbers, having an answer that lives on the other side, the geometric side, the side of circles and curvature and pi. Two rooms of mathematics that were supposed to be separate, connected by a hidden door. This is the first place in the history of math where somebody kicked that door open and walked through. Euler's proof of Basel was not only a solution to an 85-year-old problem, it was a demonstration that the arithmetic of integers and the geometry of circles were talking to each other the whole time, and nobody had been listening. Modern mathematics is full of bridges like this. The prime number theorem connects primes to logarithms. The class number formula connects algebraic number fields to special values of L functions. The Langlands program tries to unify number theory and representation theory. All of them are descendants of Euler's leap. But Basel was the first. A sum of reciprocal squares and an answer involving pi. No reason it should have been true. No reason the integers should owe the circle anything. And yet, pi squared over 6. Pietro Mengoli could not have imagined it. The Bernoullis could not have imagined it. Euler saw it first, and 3 centuries later we still teach it, because nothing else in mathematics quite hits the same way. That is the Basel problem, that is how Euler cracked it, and that is why, almost 300 years later, we still talk about it.